Assalamu alaikum. Third year secondary. This is physics session. We are in chapter 7, laser. My name is Ahmed and I teach physics. Last time we talked about the properties of laser, just a general idea, and we talked about two types of emission. We have the spontaneous emission and we have the stimulated emission. Today, I would like to talk about the properties of the emitted photons. And so today, we'd like to talk about the properties of laser. In spontaneous emission and in stimulated emission, we have differences between both of them concerning certain points. Point number one, the wavelength range or bandwidth. The second feature is wave phase or coherence. 3, the intensity of wave beam and the obedience of the inverse square law. And number 4, the collimation or dispersion of the wave beam. If we look at now the properties of the emitted photons in stimulated emission, we care about also the same features because they are everywhere. Today, we'd like to talk about the laser theory. And the lasing is simply amplification of radiation. And for this to happen, we need first to go for the mechanism of the laser theory. We start by the most important point of laser, which is how to perform or how to force the atom to emit radiation in a form of stimulated emission, not the normal one, the spontaneous one. First, we need to transfer the atoms from the normal state into an excited state, and the number of excited atoms, they have to be bigger than the numbers of the unexcited ones through a mechanism called population inversion. So to understand laser, we have to start by explaining what do we mean by population inversion. Population inversion is simply the way that we excite atoms so that the number of excited atoms will be more than the number of atoms in ground state. And this is the start point of any laser. So here the definition of population inversion, it is the state where the number of atoms in the excited state is greater than the number of atoms in the lower state, which means that the more excited atoms than the normal ones. And how amplification takes place, it's by successive multiple reflection of photons. We are going now to see how this could be achieved. How can we have reflections, many times of reflections inside the lasing material in order to produce more photons. We are going to get this when we study the structure of the laser. But simply the reflection happens between surfaces of mirrors. We have two surfaces of mirrors, and these between them, the photons will be successively reflected, and this will make the radiation amplified. Stimuli other atoms along their path to generate other photons. We mean by this action is when we have multiple reflections of photons, every one of them will stimuli other photons, other atoms, in order to be excited. So, and Stimulated emission of radiation takes place after this. So simply, what's population inversion again? Here we have two states, the ground state, as we said, E1, we call it the ground state, and we have the excited state, which is E2. Now, if there is a photon which has the energy h nu, and this h nu is the difference in energy between E1 and E2, so it's E2 minus E1 delta E, which is the change in energy. This is the same energy carried by the coming photons, and this photons, when hits the atom at excited state, it will force it to go back to the ground state, and a photon will be released. This is the stimulated emission. So as you see here, this has to be done by the two reflected mirrors. Now, to the structure, how can we construct a laser to work in industry or in medicine or in any form of research? We need to study the laser structure. Despite that the lasers are different in many things, but they all have certain components, three main major components. They are found everywhere in any kind of laser. And by knowing them, we established the idea of how to make a laser and what is the main principle of action. The structure of any laser has components. Component number one is called the active medium. Number two, the energy source. And number three, the resonance cavity. Let's take them one by one. So any laser is made of three main components. The first one is called the active medium. This is the kind of material that I'm going to use, or a substance I'm going to use their atoms as a source of laser. I'm going to excite these atoms to transfer from their ground state into excited state, and these atoms are going to produce the radiation. So we call this component the active medium. And later we will know that active medium can be solid or liquid or gas or even ions or mixture of many other things. The component number two is called the energy source. In order for any laser to work, it has to be provided with the energy, and this energy will cause the excitation of the atom. So this kind of energy is the start of the action itself, the lasing action. And the energy source can be like anything like electric or optical, or it can be also thermal or chemical, and so on. So we have many types of energy sources that could be used to trigger or start the lasing action. The component number three about laser is the resonant cavity. This is the apparatus itself, or the device. The resonance cavity, it is simply the place, the special place where we put the active medium in, which will enable the laser to perform. Let's now talk about of laser, which is the active medium. The active medium is simply the material or the substance I'm going to use to produce laser, and these materials or this substance has to be transferred from its ground state to its excited state to the degree that more atoms will be in the excited state than in the normal state to reach population inversion. So the active medium can be either solid or liquid or gas. So if the active medium is solid, example of this like Rabi laser or silicon crystal laser. The active medium can also be a liquid. And this liquid can be organic liquid dye dissolved in water, or it can be the lasing medium, or the active medium can also be gases, such as neon helium laser. It's a kind of laser that we are going to investigate in some details later. Or the active medium can also be ionized argon laser. So the active medium is not the gas, it is the ionized gas, which is the ionized argon. It can be carbon dioxide laser. So as we said, that the active medium can be solid or liquid or gas, or mixture of uh, uh, gases like helium neon or neon helium. Okay, the component number 2 about laser is the energy source, which will provide the laser with the energy necessary to excite the atoms. And we have many types of energies used to start the lasing action. So here in this table, we have the type of energy, and we have also the scientific principle and some examples. So the energy sources of laser can be electric energy or can be optical energy. It can also be thermal energy or chemical energy. Now these are the main categories of energies used for laser as a source of energy: electric, optical, thermal, and chemical. Now let's talk about the principle of each one. The electric energy, when electric energy is used to excite atoms, this can happen or achieved by two ways. It's either by using electric discharge technique or strategy, where we apply high voltage, and this will cause electric discharge, and electric discharge will trigger the lasing action. And the second way is called the high frequency radio wave. The high, the high frequency radio wave is another way of producing the stimuli to the atoms in order to excite them so that they can transfer to excited states. Example of electric energy as a source of exciting atoms, the helium neon laser, and the second one is the carbon dioxide laser, and the third example is argon laser. So we have here three lasers. All of them, they depend on the electric energy as a source of energy to excite atoms to produce the lasing action. The helium neon laser, the carbon dioxide laser, and the argon laser. Now, this is about how to use electric energy to produce laser. Now, another source of energy that can also trigger the atoms to produce laser, I can also use the optical. The other one is called optical energy as a source of um, um, stimulus to the atoms, and such as Rabi laser or liquid dye laser. In Rabi laser, we use flash of light, or we can also use the laser beam. So another laser can also produce the energy, the optical energy necessary to excite atoms. So some lasers depend on the optical energy as a source of exciting atoms, such as Rabi laser and liquid dye laser. The Rabi laser depends on flash of light, and this flash of light can be produced from any normal source of light, but it has to be intense with high energy. The second example is liquid dye laser, which uses actually another type of laser, any kind of laser, to produce the optical energy necessary to excite atoms. We have also another source of energy, which is the thermal energy. The thermal energy is also used to trigger the stimulation for laser. The thermal energy can affect moving pressure in gases. So by changing the pressure in gases, I can change the temperature, and by changing temperature or increasing the temperature, I use this increase in temperature as a thermal energy to start the lasing action. And sources is the chemical energy. The chemical energy can also start the lasing action, and it can simply be achieved by putting things together. One example of how to start chemical energy as a source of energy to produce this kind of stimuli to lasing action is the reaction between a mixture of hydrogen, deuterium, fluoride, and carbon dioxide. So the action of this is just put the mixture of gases together and let them react. And when they react, they produce energy. This chemical energy produced will trigger the lasing action and will cause the atoms to be excited. So one example of this is the chemical reaction that takes place between the mixture of hydrogen, deuterium fluoride, and carbon dioxide. We put them together, they start to react, and as they react, chemical energy will be released, and this chemical energy will be used to activate the medium or the substance to produce laser. So these are like examples of the sources of energy, different sources of energy. Now to the lasing action itself and how to arrange the device in order to start the lasing action. As you see from the diagram, we have this cylinder contains the active medium, and this active medium, as we said, can be anything, can be solid or liquid or a gas. And as you see here on the right side and left side, we have reflecting mirrors. But they are different in their reflection coefficient. So you don't have the same reflection coefficient, which means that one mirror is completely reflecting any photons, and the other one can leak some of the photons, which means that they reflect photons, but at the same time, their reflection is not 100%. So they have the ability to leak out or to allow some of the photons to get out. And actually these photons, the little photons, they penetrate the semi-transparent mirror or the less efficient in reflection mirror. This actually the laser. So the laser comes out from this mirror. So if you look here again, I'm going to just explain what's going on. The structure is number one in the cylinder, which contains the active medium. And the active medium will be subjected to energy input to cause the pumping action. So this can be obtained by any source of energy, such as electric energy or optical energy or chemical energy or any other form of energy. And as you see here from the right and the left, we have reflecting mirrors. This is totally reflecting mirror, which means that no photons can leak out or come out from it. And here you have a leaky mirror. Leaky mirror means a mirror that allows some of the photons to come out. And when they come out, they form what we call the laser beam. The place between this mirror and that mirror, it's called the resonant cavity. And it's called the resonant cavity because it causes multiple reflection, or the structure itself, when you put the photons like the active medium between two mirrors, the photons will go that direction and that direction. Can you see the arrow? The arrow is indicating two different opposite directions. So photons are coming this way and they hit the mirror and they are reflected back, and then they hit the mirror and they're reflected back, and so on and so forth. And as you see also, the mirrors are actually perpendicular on the axis inside the active medium. So the cylinder here has an axis. This is the axis, this line is the axis of the cylinder. And mirrors are put in such a way, each one of them is perpendicular on the axis, and that causes the photons never to get out between the two mirrors, and never means that they don't escape from this place unless they reach a certain degree, and then they come out from here as laser beam. So what we mean is leaky mirror has coefficient approximately like 98% reflection coefficient, which means that they don't have 100% reflection, but the other one is totally reflecting. It has like 99.9% coefficient of reflection, which means that no photons or nearly no photon can escape or can leak out from this mirror, but some they escape from this mirror, and these escape photons, they form the laser beam. So again, you have the active medium, number one, component one. Component two is the source of energy, which will be provided. And number three, the resonant cavity, which mainly contains two mirrors with different reflection coefficient. Now we go back here to explain simply by another diagram the same structure again. This is the laser material. And here the arrow indicates the direction of reflection. See, this arrow goes from left to right, hits the mirror. This mirror is partly transmitting mirror, which means that it's not 100% reflecting. But here you go, you have the photons coming this way, it hits the mirror, got reflected as I point here, and it hits that mirror and reflected, going this way, this way, this way, until it hits the mirror again, and then back again to the opposite mirror, and then hits back again, again, until it hits this, and then back again. So as you see here, photons will have multiple reflection between the two mirrors. Here is another structure of another laser where I use the optical pumping. What I mean by optical pumping is that we use the energy from light or optical energy to cause the excitation of atoms. And we call this, so optical pumping means using the optical energy, mainly light energy, to cause the excitation of the atom. In this case, I used a flash lamp. Just this is the flash lamp, and I will use it as a source of energy. So this is the lasing material. It could be a crystal here, and here the flash lamp. This will what will cause the energy to go inside and excite the atoms. Here you have the partially reflecting mirror. It can be it can be a plane mirror, or it can also be a concave mirror. And here you have the highly reflective mirror. This is like 99.9% reflecting coefficient, which means that it reflects most of the photons. And here we have the optical resonator. The optical resonator is the resonant cavity, which is the same. It allows the photons to go between or reflect between the two mirrors. And some of these photons will leak out, and these leaked out photons will cause the laser output. Now, if we go and discuss a specific type of laser, we have discussed the general idea of any laser, the structure and how it works. But we need now to have a specific type of laser, and we investigated in some details about the structure and mechanism, how it works, and so on. So we choose here the helium neon laser as a kind of laser to investigate further. We take the first part is the structure. The structure of helium neon laser. As in any laser, we have the active medium, and we have the source of energy, and we have the resonant cavity. Let's take each one of them now, and we talk about specifically about helium neon laser. Okay, in helium neon laser, as you know that helium is a gas and neon is a gas, both of them noble gases. We use a mixture of them, and we put them in a tube, and this tube made of quartz. So we get quartz tube, and we put inside the quartz tube mixture of these two inert gases, helium and neon, but they have to be in a specific ratio. We use more helium than neon. Actually, the ratio between them is 10 helium to 1 neon. So a mixture of the two gases, the ratio will be 10 helium to 1 neon, and we put the mixture inside the quartz tube, and we keep it at low pressure. Low pressure is approximately less than half millimeter mercury, 0.6 millimeter mercury. So here you have a mixture of gases in a specific ratio under a very low pressure. The part number 2 of the laser is the resonant cavity. In the resonant cavity, we have external mirrors. The reflecting coefficient of one is 99.9%, and a semi-transparent mirror, 98%. So this is the two mirrors that they are going to cause the multiple reflections, which will cause the amplification of the action. Number 3, the third component is the energy source, which is in this case the electric energy, and we can use electric energy in two different ways. It's either by electric discharge or high frequency electric field. Simply, how to cause the atoms to be excited, we apply high voltage. If we apply high voltage, now atoms will be excited, and when they are excited, the lasing action will start. Now, these are the components of the laser, helium neon laser. Now, let's talk about the operation. Operation means the mechanism, how it works. I put here the mechanism of working of helium neon laser in a form of steps clearly identified. Let's now talk about how it works. First step is we need to excite the atoms. So first we apply the high voltage. High voltage will excite the helium atoms. And after the helium atoms are excited, they collide with the neon atoms. So you have two atoms, two types of atoms. You have helium atoms and you have the neon atoms. Applying high voltage will excite the helium atoms first. So helium ions will be excited. And when they are excited, they start to move with high kinetic energy, with high speed, and then they collide with the neon atoms. Now, resulting from this collision, because it's inelastic collision, when helium atoms they collide with neon atoms, the result is the transfer of energy from the helium atoms to the neon atoms. Once I have inelastic collision and the energy transferred from helium atoms to neon atoms, now neon atoms also now they will be excited. And that's what we want. We want to excite neon atoms because they are the substance that I'm going to use to produce the energy of the laser. So what happens is when I have more neon atoms excited, I will reach the start, which is the population inversion of the neon atoms. Now, population inversion, as we said before, it's achieved when the number of atoms in the excited state more than the number of atoms in the normal state. This is called population inversion, and we are going to use this to cause the lasing action in neon atoms. So by this, the neon atoms has a metastable state. This is one thing that's very important. Now, what we mean by metastable state, it means simply, we know before from the last lesson that the lifetime, which is the time taken for atoms to transfer from the excited state and return back to its normal state. We know that this time is 10 to the power of -8 of a second, which is very small time. But in metastable states, this time can increase 100,000 times, which means that the lifetime can be 10 to the power of 3 of a second, 10 to the power of 3 of a second. And this is relatively longer time than the normal one. So as you have here, this is 10 to the power of -3 of a second. We call this metastable state. What we mean by metastable state? It's a state where atoms in the excited version, they have longer lifetime than normal. The normal lifetime 10 power -8. Now, in metastable state, they have approximately 10 to the power of -3, which is compared to the previous one, a long time. Now, imagine now what will happen if atoms, they stay in the excited state a little bit longer. So they will have a chance to be hit by other photons. And this kind of hitting will happen before they finish their lifetime. And if this happened from previous lesson, we know that if this happened, the atom will be stimulated to radiate photons, because stimulation means that the atom will radiate the photons before the end of its lifetime. And this radiation will be stimulus radiation and will have the same phase and will have the same frequency of the falling photons. But actually also what happens is another type of radiation, which is spontaneous also. So spontaneous radiation of neon will also take place when they release some of the photons in random direction. So they got excited after the lifetime, they come back, the atoms, they come back from the excited states to the normal states, and they will radiate spontaneously emission. And these atoms, these photons is radiated spontaneously from the neon atoms. They make the atom less energetic, they less excited, and they go in all directions. While these photons, they go in all directions, they also cause collision of other unexcited atoms, causing their excitation, which means that the chance of hitting more atoms will increase, which will increase the pumping action or multiplication. So here we say the spontaneous emission from neon takes place, and that releasing many photons in random direction. This is happening because of spontaneous emission and not because stimulation. And these photons collide with neon atoms in the metastable state before its lifetime finish. So which means that this collision happens while the atoms are excited and before the end of their lifetime. And this causing stimulated emission from neon atoms. The point number 5, the neon atoms eventually loses their excitation and return back to the normal unexcited state. And that's logic. By continuous emission of radiation from the neon atoms, eventually at the end they will reduce, their energy will be reduced gradually until they come to the ground state. One diagram here shows how the helium neon laser acts. So here you have the helium, and here you have the neon. The reason why we use helium and neon and why it is causing this kind of lasing action is because when helium and neons are excited, they have close energy level with each other. Like they are close in energy level. That's why the transformation of energy between helium and neon, when helium loses energy to neon, it could be easier because they are close in their energy levels. So as you see here, helium got excited. So As you see here, electrons, they can go from ground state into higher states. And after a while, the neon will also, due to this collision, will have high energy. And when they have high energy, the ground states will now, the atom will go to higher excited states and they will come down to a lower energy state like this one or that one, and they produce energy. They produce in the form of radiation. Now, in this diagram, this is the helium ground state. This is the metastable state. Okay, can you see here? This is the metastable state, which is excited level of energy. But the metastable means that the lifetime that's spent here higher than the normal normal. It's approximately 10 to the power of -3, as we said, which is longer than 10 to the power of -8, which is the normal state or the normal lifetime for atoms to be excited in. So which means that after collision, this is the collision between helium, collision here, to the neon. This is the ground state. And here you have two types of radiation. Okay, you have a spontaneous emission, and you have also laser transition, which is the stimulated emission. Can you see here? You have here one photon here and one photon here, and these two photons, they are coherent with each other, and they have the same phase, they have the same frequency, and they cause the lasing action. So this is how the neon laser is produced. And next time we'll we talk about applications of laser, mainly holograms and so on. Some of the most important application of laser. By this we come to the end of our lesson for today. Thank you for listening. Don't forget to drop any question or anything that you'd like to ask for. Thank you for listening, and see you next time. My name is Ahmed and I teach physics.